Okay, I think we'll go ahead and get started. I'd like to welcome you all back to the Breakthrough Seminar. My name is Jeff McDonald, and it's a pleasure to welcome you. As always, want to thank Howard Weeder and the Canada Excellence Research Chair for funding this program, and welcome our simulcast viewers from around the country and around the world. And also to alert you to next week's speaker, who is Amilcar Porperato from Duke University in North Carolina, who will be here talking about soil, water, and climate. But today it gives me a great pleasure to introduce Kamini Singha. Kamini is Associate Director of the Hydrologic Science and Engineering Program at the Colorado School of Mines and Associate Professor in the Department of Geology and Geological Engineering. She's been there, I think, for the last 2 years, and prior to that she was Assistant and Associate Professor at Penn State in the Department of Geosciences. She got her PhD in 2005 at Stanford University in hydrogeology. And in the 9 years, I think, since obtaining her PhD, she's really gone to some great heights. Her work has been noted with many awards, teaching awards at both universities where she's been teaching, outstanding faculty member at Colorado School of Mines, the Penn State College of Earth and Mineral Sciences Wilson Award for Excellence in Teaching, another Atherton Award for Excellence in Teaching, and I think you'll see a great example of that in today's talk. She was also NSF Early Career Award Scientist grant given to you around the time of your PhD. And she's had much service to the community. She currently serves on a National Academy of Science Committee on Subsurface Characterization. She chairs the AGU Hydrogeophysics Committee, and I think quite significantly for someone at her career stage is Associate Editor for Water Resources Research and also Associate Editor for Vados Zone Journal. So it gives me great pleasure to have Kamini Singha with us today, who will tell us about some geophysical applications in hydrology. Kamini.
Well, thank you so much for the kind introduction. It is really great to be here, my very first time in Saskatchewan. And what I'm going to talk to you guys a little bit today is about the idea of transient storage, the idea that something is being held in a hydrologic system for a certain period of time, hence its name, transient storage, and how I think that geophysical tools can help us answer some really interesting and important questions that exist within this idea that we'll see in multiple different hydrologic systems. So before I get going, I just want to thank a lot of people before I get started, so you recognize who's contributed to this work, and in particular Mike Gusev, a colleague of mine at Penn State who's now at Colorado State and actually moving to the University of Colorado, and Adam Ward, who is a PhD student working with us, who's now at Indiana University, and some associated other folks and money without whom and which this would never have happened. So I'm going to start off by talking about streams today, and I'm going to take us on a tour over to groundwater and then back to streams is the goal for today. But what I want to talk about is transient storage in the context of stream systems. And the idea is that if you think about a stream system, there's this zone that some of you I know have heard about because we talked about it this morning and may be familiar to many of you and new to others, which is the idea of a hyporheic zone. And that's this area here in this, oh, that's a black screen, area around the stream here that's labeled as hyporheic zone. And it comes from two Greek roots, hypos meaning below and rheos meaning flow. And what this is it's an area in a stream system where surface water becomes groundwater and then becomes surface water again. Now, the reason you would care about this is that it's a biogeochemical hotspot. There are high gradients in things like dissolved oxygen and organic matter, and what that means is bacteria are going wild in that little zone around a stream, and all of the good things that streams do for us, like denitrification processes and metal uptake, happen because of the increased residence time associated with that hyporheic zone. And it's been called a river's liver, for example, in certain papers, which I think is a pretty good descriptor of what this thing does. What's great about hyporheic zones is that they increase the residence time of fluids, and so what that means is that there's time for some of these processes to happen. So when we talk about these systems, we talk a lot about transient storage, the idea of something being hung up in the aquifer surrounding a stream. So if we were interested in how to characterize that zone, usually the ways that we go about it are few-fold, and one of which is you and your best friend go get a big bucket of dye, and you go out there and you put a little bit of that into the stream at a time, you do some sort of test, and based on a downstream concentration breakthrough curve, you try to figure out what must have happened in the aquifer surrounding the stream. So you say, well, this happened in the stream, and so consequently, this must exist around the stream. That's the first way that we do it. The other option is what I might call aquifer acupuncture up there. And so what you have is a certain number of piezometers that you would put around a stream to try to say something about where that dye moved. Those are sort of our primary options for saying something about transient storage processes and understanding what's happening in stream systems. Now, just to give you a sense of what happens in these systems, this is a sort of classic advective, dispersive, diffusive curve. So this is a concentration history, concentration with time plot for something that is moving through a hydrologic system. It's advecting, moving with Darcy's law, and it's dispersing. It's spreading as a function of the fact that stuff is in the way. And you get this quasi-Gaussian curve in terms of concentration and time. It's Gaussian in terms of concentration and space. But what we see in these transient storage systems, like these stream systems, is something that looks more like this, which is that you effectively have two concentration histories. There's actually a whole suite of them, but let's think of it as two systems. One for the connected pore space, which is this dark line here, so the connected part of the system, so the stream itself. And then that dotted line, the one we can't really measure very well, which is for the less mobile part of the system, so the aquifer itself or the dead-end pore space. We have a harder time measuring that dotted one. We do really well with measuring the solid one. We're in stream, we measure the concentrations coming through, and then we try to infer the dotted one. In either case, what you notice is that in the transient storage case, we have a very long tail compared to the classic advective dispersive sort of behavior. And that's because stuff's getting hung up. And some of it is taking a little while to get into that aquifer around the stream, and then even longer to discharge. So that's the idea of that dotted line situation that's happening there. Interestingly, though, we see this same behavior in groundwater, even when we don't have a stream involved. And an interesting data set to sort of highlight this is from the macro dispersion experiment site in northeastern Mississippi in the southern United States. And here's some data that are quite old at this point, but I think open an interesting conundrum in groundwater transport processes. So up at the top, what you see are data from a tracer test that was conducted. This is a tritium tracer test, so something that's supposedly conservative, meaning that it's not reacting, it's moving with groundwater. And there's a whole bunch of well data that go into making that isosurface plot. And what they did is they injected this tracer into the ground and came back a year later, and what they found looked like that. So some of the tracer has moved down gradient, but a whole bunch of it is sitting right where they injected it. And in fact, if you look at this in terms of mass, which is the bottom curve, what you see is that most of the mass is sitting right where, basically, it was injected. That's okay, right? We can think of a lot of reasons for that to happen. But here's where the conundrum happens, which is really cool, which is that when they calculated mass during this tracer test, at early time, they calculated too much mass. At late time, they calculated too little mass. Too little mass is no problem for hydrologists, right? We're really good at losing mass. Put something in the ground, who knows where it goes. But too much mass is hard, right? That's physically impossible. It'd be amazing if we could do that, right? We could put gas in the ground to get more gas back out. It would be great, right? But so there's a question about how that could be. So hypotheses that came out of that work and others was that there's a transient storage process happening in groundwater. And we can think of the world as having two types of pore space. Whereas if I take my aquifer system, I could break it into, say, two or more systems, where I have a connected pore space. So up here at the very top, I'm trying to highlight in blue pathways, say, that are highly advective, where the pores are connected really well, so material can move easily. And then down here in sort of this red pore space, where there's a more dead-end, poorly connected pore space. There's no advection happening via Darcy's law, and stuff is getting in there via diffusion or some sort of slow process. And so consequently, you have transient storage in a groundwater system too, in this case caught up in that less mobile pore space. So whether we're talking about streams or we're talking about groundwater systems, there are places where stuff moves and places where stuff doesn't move so well. And that's the idea of a transient storage type process. So if I come back to the macro dispersion experiment site, this was sort of the explanation of the mass story that I was trying to give you guys. So let's take a block of aquifer that we see up there at the top, and let's put through our tritium tracer. So at early time, what happens is that if I go in here and I dump a well inside of this upper box, and I pull a sample of concentration out, I'm going to get tritium, right? Because tritium is moving through the blue part of that system right now. And if I say, well, that tritium concentration applies to the support volume of my measurement, to that entire box, I would estimate a mass that was much too high, because I would assume that that concentration applies to this entire pore space, when truthfully it's only in the connected pores. At late time, my tritium is gone. It's out of my advective pore space. It's diffused into some of the dead-end pores, but I can't sample those with a well. When I put a well in the ground, what I pull out of a well is what is preferentially mobile. So I sample this lower pore space now and I get 0 concentration. And I think, oh, all clean, right? But truthfully, you can see that there is still stuff stuck behind in that dead-end pore space. And so my estimated mass would be too low. So that was sort of the story that people had come up with for the transient storage piece of the macro dispersion experiment site. So the thing about transient storage is it introduces a few more free parameters in our models. And that's part of the reason that we have some trouble using these models, is that we have a hard enough time with the upper equation, which is just a classical advection dispersion equation. What this equation says is that if I'm interested in tracking the concentration through time in my mobile, my connected pore space, well, it's a function of a couple of things. It's a function of advection, as controlled by Darcy's law, hydraulic conductivities and gradients, and it's also controlled by dispersion and diffusion, which go into that term right there. If I'm interested in some sort of transient storage type equation, and you'll see variants on this equation, this is just one, and a commonly used one in groundwater, but very similar equations exist for stream aquifer interaction. The white parts are exactly the same as above. I have a mobile pore space, there's advection dispersion happening, but now I've got some new equations which are red, which are a little hard to see in this light, I'm sorry. But what it says is that now what I'm doing is I'm tracking not only the concentration in the mobile pore space, but I'm tracking the concentration in the immobile pore space, the stuff that I can't easily sample. And how much concentration is in that immobile or less mobile pore space, meaning the hyporeic zone of a stream or the dead-end pore space in groundwater? Well, it's going to depend on how much of that space exists. So in this case, I'm showing you the porosity of the less mobile domain. We could think of it as the area of the hyporeic zone. And then some sort of mass transfer rate, alpha here, which looks something like diffusion over a length scale squared. And the difference in concentration between my connected and less connected pore space. The important part about all these equations is not that you understand these equations, but that you realize that there's more pieces. Up here, we're trying to figure out things about dispersion and porosity, which are hard enough for us to estimate and put into models. Down here, I still have porosities and dispersions, but now I have immobile porosities and mass transfer rates, things that I have a very hard time measuring. So while these models do a better job of fitting our data, in terms of predictive capability, we have a lot of trouble estimating those extra parameters. And when you think about Earth systems, we have these very simple conceptual models we're trying to fit about mass transfer, meaning stuff moving from connected to disconnected pore space or from streams to aquifers. But when we look at Earth systems, they're incredibly complex. If I was going to draw flow lines on this map, they're all over the place. The residence time of solutes in a system like this are incredibly complex. They're not as simple as connected and disconnected, but that's what we're going to talk about today to make our lives a little simpler. But understand that, clearly the Earth system is even more complex than the simple transient storage model that I just highlighted for you. So this got me thinking. I have an undergrad degree in geophysics, and I still have a special place for it in my heart. And I started thinking about the relationship between fluid flow and electrical flow. So when I take a sample with a well out of pore space, I am preferentially sampling what it is that can move easily. So there's all this dead-end pore space that I can't easily pull water out of a system with. But geophysics isn't that smart. And so it turns out that what might be less mobile or immobile to something as large as a water molecule may still be connected electrically. Current goes wherever it wants. And so what's great about electrical methods is that they are sensitive to the total dissolved solids, everything that's in the system, whether it's sort of connected hydraulically or not. And so that got me thinking about whether or not we could use these sorts of data to say something about that less mobile concentration piece, the thing that we can't measure very well in the field. So just as a one-slide primer on these tools, the way they work, this is like the lowest tech geophysics. It's a great tool. For those of you that have seen seismic methods or other electromagnetic methods, this is really low tech. The way this works is you're going to stick a couple of electrodes in the ground. And when I say electrodes, those of you that are in geochemistry might think something really fancy. When geophysicists say electrodes, we often mean stakes of rebar. Right? So what I'm going to stick in the ground is a couple pieces of rebar. I'm going to pound them in with a sledgehammer. I'm going to attach 2 pieces of rebar to a car battery, and another 2 pieces of rebar, I'm going to measure the resultant voltage. There's a little more into that with the current and some other things that are happening, but essentially, battery, rebar, voltmeter. And so what you're going to do is you're going to drive a current into the ground, and that's what's being shown here. And then you're going to measure the resultant potential drop between 2 electrodes. And then from that, if you go back to like freshman year physics, you remember Ohm's law that said V is equal to IR, voltage is equal to current times resistance. If I know the voltage and I know the current that I'm injecting, then I can back out the subsurface resistance. Now, why would you care about resistance? Well, resistance turns out to be correlated to lots of things that hydrologists are interested in. Resistivity, which is a property of a material, or its inverse conductivity, which you're used to probably thinking about more, tells you about how easily electrical flow, or in the case of hydraulic conductivity, water moves. And those two things are related to each other. Electrical conductivity will tell you how well connected pore space is, the salinity of that pore space, things that you might actually care about as a hydrologist. And what people tend to do, sort of the state of the practice with using these methods, is to look at the bulk conductivity, which was what we're going to measure with these geophysical tools, and compare them to fluid conductivity measurements that we would make in samples or by hand with EC probes. And generally we say, oh, well, there's a straight relationship between these two things, this linear relationship via Archie's law. So that means if I know the bulk conductivity in some system, then I can back out the fluid conductivity. And so if I'm interested in a saline tracer test, then I use this instrument that does all this stuff for me, and I back out what's happening everywhere at all locations in terms of the fluid. And so that is one of the reasons that people think geophysics has a lot to contribute to hydrogeology. So let me tell you a story about aquifer storage recovery and how these ideas, these tools, and this idea of transient storage play out in a system. So aquifer storage recovery is sort of an engineering idea to take water during times of surplus and put it in the ground. So during snowmelt, there's a whole bunch of water that's coming out of the mountains, out of the systems that have had snow on them, and maybe we want to store that for some period of time. And putting it in the subsurface means that we don't have to deal with the evaporative losses of surface reservoirs. The problems, of course, is that there's some engineering questions about putting water in the ground. Where does it go? Are you going to come back in a year and find that it's migrated somewhere else? How's the chemistry changed? Usually what you're doing is putting fresh water into an aquifer that's not as of high quality. These sorts of systems, these ASR systems, are used mostly in arid areas or in coastal environments. So often your freshwater bubble, as they call it, is going into a brackish aquifer. And so there's lots of questions where if you have this ASR borehole that you're injecting your fresh water into, what happens along the edge in terms of the mixing? So you're losing water quality potentially if you're putting that fresh water in. So you store this thing for some period of time, however long you want to do that, and then you pump it back out. There's also biological questions, which are a whole other can of worms, can of bacteria. So then we're going to pump this thing back out. So we looked at an ASR site in Charleston, South Carolina, on the southeastern coast of the US. It was an emergency supply for the town of Charleston in case of hurricanes. And so they were injecting water into the subsurface, and we're sort of curious about these physical, biological, chemical questions. So we did a really small-scale pilot test. It turns out, you're not really going to do aquifer storage recovery over 9 days. Usually, you could probably figure out a better way to store that water. But this was sort of a short-term test that we were using to answer some questions that the U.S. Geological Survey had about the site. So what I'm showing you here is some very low-tech geophysics. I have 4 electrodes inside of a fractured limestone aquifer, and all I'm doing is driving a current, measuring a potential, and estimating from that how the apparent conductivity is changing as we inject this potable water into a salty aquifer. So what you see from 2 different observation wells is the following. You see that at early time in both of these plots, you start off with a high bulk conductivity, salty aquifer. You inject some fresh water, that decreases. We inject water for 5 days. We store for a couple days. Not much happens, and then we pump it back out. That is like the least exciting data set that you will probably ever see. Right? Here is what is really cool. Here's the fluid conductivity data from the same location. So we have a tube going down the borehole. At this point, we're actually pulling water samples up to the surface. What we see looks almost exactly like what we see in the geophysics, but in the water samples, what we see is actually one thing that's distinctly different, right? Which is that you see this interesting rebound behavior here. So as soon as we turn the pumps off, all of a sudden we get more salt. Well, that's kind of interesting in its own right. And so it led us to talk about, and we see this in both observation wells, led us to talk about what was happening in the system. And what we thought might be happening is that you've got a system that's very highly advective when the pumps are on. Water is really moving. And then you turn the pumps off, and the system relaxes, has a chance to sort of breathe. And all of that salty water that's trapped inside of that dead-end pore space, that less connected mobile pore space, sort of starts to breathe back out, diffuses back out, and into the mobile domain where we can sample it. The geophysics doesn't see it because it doesn't know the difference between what's connected and what's not connected. To it, everything is connected. The same amount of mass has always existed that was there. Here, because we're sampling only what can move freely, there's a big difference between what's connected and what's not. At least it's a hypothesis. What's also interesting is that if we plotted then the bulk versus the fluid conductivity, like I showed you a second ago, we don't see a straight line relationship. We're not exactly breaking Archie's law, but what we are doing is breaking our understanding of the processes that are happening within this system. because we see this really interesting hysteresis between the two. So there's some sort of lag effect that is certainly happening between our bulk and our fluid conductivities. So here's the hypotheses that we came up with. So we basically said at early time, what's happening is that we're injecting this fresh water into the aquifer just as we expected to do. And then during storage, here's where something interesting happens. It's not the edges of the bubble. It's not only the edges of the bubble that we need to worry about. So it's not just here on the edge where the fresh water is actually mixing with the brackish aquifer, but it's inside of the bubble. Because what happened is we put all that fresh water into the aquifer to store it, and then what ended up happening is that all the salty water that was in the less connected pore space starts to have time to exchange. So we start degrading our freshwater bubble from the inside because of less connected pore space. And that is actually what we see in that rebound. So what happens is we no longer have such an advective system. All the salty stuff that was sort of trapped in here during pumping starts to come out of its dead-end pore space, leading to that rebound, and then we pump the water out. At least that was an idea. So we made some models, at least to test the idea that's happening here. And so these are three very complicated plots, and I'll walk through them here in piece at a time. But what these are some 1D radial models using ModFlow and MT3D, two very simple, straightforward codes. And what I'm showing you are three things. I'm showing you our predicted fluid behavior, the fluid conductivity with time, the predicted geophysics behavior, the bulk conductivity with time, and then the hysteresis between the two. The white curve is basically what I'm calling our base case scenario. It basically describes most of the variance in our data. Given that this is a 1D model, it's not too bad. We have nothing in here that's particularly complicated. And in the white model, what you see is that rebound that we see in the flow model, not a whole lot happening in the geophysics, and then a hysteresis curve. It's not perfect, but it's not so bad. So what I wanted to know is, what if we tune the dial on one of those parameters that we have trouble measuring, like that mass transfer rate that describes how quickly stuff can move back and forth between the connected and less connected pore space? Well, let's turn it way up. Let's go to the blue curve to start. If I turn alpha up, and that means that now stuff can exchange really freely between whatever's connected and what's not so connected, then what ends up happening is we see that the fluid behaves just like the geophysics, because there really isn't a less mobile pore space anymore. Stuff is moving back and forth so freely, it's kind of like having one connected pore space again. And what you'll notice is that this curve starts to collapse back towards a straight line relationship. So when things move easily and quickly between the two things, there's not really transient storage, is the punchline. What about the red curve? Well, here what's happening is we're turning down the mass transfer rate. So we inject water into that mobile pore space, but over the time of this experiment, it doesn't have quite the same amount of time to get in to the dead-end pore space before it's pumped back out. So we see a smaller change in the geophysics. And interestingly, this line is also collapsing to a straight line, but one with a different slope. In this case, what's happening is it's almost like there is no less mobile domain because we don't have enough time to sample it. Stuff isn't actually getting in there over the time of this experiment. So there's still a relationship between the bulk and the fluid conductivity, but there's a different amount of available porosity. In one case, in the blue line, it's whatever was connected plus the not so connected pore space. And in the red line, it's just the connected pore space. So at least what this says, the who cares part of this plot, is that if you have these geophysical data and you have the fluid measurements, then you can start to constrain some of these parameters in these models that we otherwise don't have good data for. So that was part of why we thought this was interesting. So then the next question was to come back to these systems, to stream systems, and think about transient storage in these sorts of systems. So there's a few open questions that when I started this project with Mike Gusev, who's in Colorado now as well, some questions that we asked ourselves were, how do streams exchange with their aquifers, and how does that change depending on a couple of variables? Here is actually a plot that came out of our proposal, and we had the following sort of hypotheses. We said, well, maybe at times of high base flow, where we have, early in the system, when we have lots of flow within our aquifer and we have high water tables, so spring, think, maybe what's going to happen is there's going to be so much sort of compression from the sort of surrounding water table around this stream. We see this water table here pushing in on this little stream. Maybe the zones of exchange are really small because it's all being squished together next to that little stream. And so we'll have a smaller zone of transient storage, a smaller zone of exchange than, say, later in the season where the water table has relaxed. And now there's no longer this sort of confining pressure of sorts on this aquifer, and we'd have a bigger zone of exchange. It was a hypothesis. The other thing that we thought about was, what about the slope of a stream? So depending on how steep that slope is, would probably control how much flow you see in the cross gradient direction. So you're going to have flow obviously going downstream, and you have a certain amount that's going perpendicular to that, depending on the slope of the stream. So obviously, if your stream is really, really steep, you might expect less exchange between the stream and the aquifer than if the stream was kind of flat. These were hypotheses that we thought we'd test. And what we were going to do is try to use the geophysics to answer some of these questions, because it's hard to see otherwise what's happening in the subsurface. The thing about stream systems is now I have to use slightly more complicated geophysics. I actually have to reconstruct models. I didn't have to do this in the groundwater system because I could kind of pretend that, that it was homogeneous and that I didn't need to reconstruct a model. But here I have a very distinct stream sitting inside of an aquifer system, and I'm going to need to reconstruct models to do this. So we're going to have a short primer on geophysics just as a reminder, or as new information for those of you that are thinking about it, about model reconstruction. For those of you that do inverse models in hydrology, hydrologists think about the inverse problem completely different than geophysicists do. In hydrology, what happens is, let's say we have 100 measurements of hydraulic head and we're interested in the hydraulic conductivity. What we often do is parameterize our system into 3 layers, and we're like, oh, I want the K of the top, the middle, and the bottom layer from these 100 measurements that I have of head. So what we tend to have is an underparameterized problem. 100 data, 3 unknowns. Geophysicists go the other way. We collect 100 data points, and then we say, oh, I want to know what the subsurface is on 10 million little pixels. So that's a problem, right? In the sense that it's hard to come up with a unique solution when you've got more unknowns than you have equations, right? Remember linear algebra. If I told you x plus y is equal to 5, there's an infinite number of solutions that could go into that, right? Geophysics is constantly fighting with that battle because of the way we parameterize our models. So what I'm showing you up here is field data. So back in the 50s, before we had computers to do image reconstruction, what people used to do is plot what are known as pseudo-sections. And the way this thing is it's just your data, and as you move your sort of electrodes around, these 4 electrodes, the 2 that are driving current and the 2 that are measuring potential, you would assign that measurement to a location in space. Now, it's kind of ridiculous, right? Because this is a volumetric measurement, just like flow. I mean, the equations for fluid flow and electrical flow are exactly the same. I wouldn't do a pump test and assign that K value to a point in space. That's effectively what's happening here. And so what I'm going to do is I'm going to take each one of my measurements. So if my electrodes are here, I'm going to put a little point in the subsurface, and I'll move my electrodes farther apart, and I'll put a deeper one. And that's kind of what this thing is up here. It's a plot of my data. And what you ultimately want is your model to produce observations that look like your field data. Right? And so you don't know exactly what depth these things are at, because that's something we have to do via inversion. But if you can get your model to look like your field data, the output of your model, then you say, well, at least the model that I used to create these observations must be plausible. It must be a model, at least, that describes the subsurface. So that's sort of inversion in one step, is that I want to get to a plot of depth and distance that shows all these pretty colors, which are electrical conductivities, where my field data and my model output look about the same. So then what happens is that we're at this middle box here. This is my inverted map of electrical conductivity. There's a minor problem with this, though, right? As a hydrologist, we don't care really about electrical conductivity or seismic velocity or dielectric permittivity or any of the things that geophysicists measure. What we want to know is concentration of something, moisture content in the subsurface, hydraulic conductivity, any number of things that we can't measure with geophysics. So what we measure with geophysics is like, bulk conductivity, shown here in green. The color scale is supposed to indicate some other property than what we're interested in, which might be hydraulic conductivity. The other thing is that while we might be able to build a relationship like Archie's law that changes my bulk conductivity to a fluid conductivity or something else, the content is not the same. My truth, whatever is in the subsurface, has much more structure than what we see in the geophysical image and the resultant output that we get using some sort of relationship like Archie's law. And that's just because, in this case, we're talking about diffusion-based physics. You're just losing a lot of data. So when you see geophysical data, think about the fact that it's too blurry. It is like the beer goggles version of what's happening in the subsurface. This happens for a couple of reasons. The first reason that this is going to happen is because of the inverse problem, which I talked about a second ago. So the idea is that if you have a similar number of unknowns, you have a little source, you have like seismic data, for instance, you have a little seismic source, and you measure the time it takes to arrive at a receiver across some little, parameterized earth this way, and if you have the same number of data as you have unknowns, then you are in great shape. But what generally happens in geophysics is that we've got some data, they go through some parts of the earth, but we're not quite sure where, and we're trying to figure out parameters based on how we want the world to be. So that's the first problem, is just the fact that our inverse problems are not well determined. And the other thing is that our measurement sensitivity varies. Depends a little bit if you're talking about, in this case, we're talking about diffusion-based physics, but there are also a lot of wave-based methods like seismic and ground-penetrating radar that you guys may have seen. They have different sensitivity maps, but the sensitivity varies in space. So this is a borehole measurement, and it's showing that the sensitivity for these electrical measurements are really high near the electrodes, which is true. And as you get away from the electrodes, your sensitivity to what's happening in the subsurface drops off. So to keep in mind that you aren't able to see with the beer goggles as well everywhere in the subsurface as you are in some places. What this means is when you put these couple things together, that if you did a little model that said, well, I'm looking for some high conductivity target inside of a low conductivity background, here's my fake tracer test, then what I'm going to get back is only going to be so good. So that's just sort of the truth of geophysics. So we have to keep in mind when we're looking at these things that there's certain limitations to these tools. And that's coupled with the idea that we're just measuring the wrong thing, period. All right, so let's take a look at some real data with all these caveats in place. So coming back to those hypotheses, we were interested in stream steepness, and we were also interested in a seasonal story about how exchange changed with season. So we looked at two different watersheds, one that was sort of a wide, flat sort of watershed in Pennsylvania near where we were working at the time, and then a sort of narrow, steep watershed at the H.J. Andrews in Oregon, because it's such a long-term research site, there's so much data there. And what we tried to think about is what we expected the down valley and cross valley components of flow to look like, both during sort of high base flow and lower base flow sort of parts of the season, for both this narrow, steep piece and this wide gradual. What I'm going to do is I'm actually going to show you just some data from the H.J. Andrews, and I'm going to show you a watershed that actually transitions from being very steep at the top to very flat at the bottom, to sort of show you all stories without having to bombard you with two data sets, just to make it a little easier. So we're going to focus on the H.J. Andrews watershed, and I'm going to show you sort of a steep, narrow story that goes into a wide, gradual story, so that we can get both pieces out of one data set. So we worked in watershed 3. This is just an image of what that looks like. It's a pretty, it's a pretty treed over system. It's got a lot going on, a lot on the ground. This is a stream that's fairly laterally confined at the top, and then as you go down to the bottom of the stream system, it opens up a little bit. It's about a kilometer square in terms of the area of this watershed, and it's fairly steep. You see about a 12% grade on the slope that we're working in. Contrary to everything that they tell you to do in hydrology, the flow is going up and to the left in this image. So its flow is going this direction. And this is an image that came out of Oregon State, of the watershed 3 watershed. And part of the reason we wanted to work here was that there was already a lot of instrumentation in place. All of these little red circles, which are hard to see, are piezometers that someone else had already put into this watershed. So no small amount of work was put into that already. And then what we did is we installed a whole bunch of geophysical electrodes. So all the little yellow crosses you see here in these 6 transects are us in terms of collecting these geophysics. Now, what we wanted to do was do some sodium chloride tracer tests, some conductive tracer tests, and off the edge of this map, another 100 meters, we injected a whole bunch of salt, and then we watched it migrate through these transects that we were interested in. One of the things that's kind of interesting is it doesn't look like very much right now, but here on the second transect, there's a little boulder here that shows up in this drawing that someone else made, and it actually shows up. It shows up a little later, so I'm just pointing this out to you that it doesn't look like much with all the other boulders that are here, but it turns out that that's actually kind of an interesting story that I'll come back to. The other thing is I'm never going to show you this transect right here, and that's because you'll notice that many of these electrodes are on rock. Turns out it's very hard to get good electrical contact with rock. Probably should have figured that out in advance, but anyways, we had a lot of trouble driving current on that transect, and so consequently the data aren't that great, so you're never going to see it. What we did is we did 4 tracer experiments at different times of year. So this was from 2010, and I'm showing you discharge here through time. What's really nice about Oregon is it's got this Mediterranean climate where there's lots of rain, and then it stops raining, and it just stays not so rainy for the rest of the summer, which makes sort of predicting discharge a little bit easier than, say, in the east, where we had rainfall all summer long. We're going to do tracer injections here at 4 different discharge rates. And this is a small stream. You'll notice by the units, we're talking liters per second. So by the end of the summer, this thing is sort of ankle deep. Okay, so what I'm going to show you here are 3 of those 4 tracer tests. I just keep cutting things out. One of the 15 liter per second case I'm not going to show you in this case because we had a pump issue, and so we injected a little too much salt. Doesn't matter at all for interpretation, but since I'm just showing you qualitative images, it's distracting. So I'm going to show you the other 3 tracer tests here, and what I'm going to show you are the reconstructed electrical images from those tracer tests. So, for instance, this is 3 hours into the injection at 33 liters, 7 liters, and 4 liters per second, and you can see that something is lighting up. That's the stream. It's full of salt right now, 3 hours in. And what I'm going to do is I'm going to migrate through here in time, and you'll be able to see how this propagates through time. And one of the questions we were interested in, again, remember, is the size of that hypereic zone. And we had this idea in our heads that in early season it might be smaller because of confinement, and at late season it might be bigger. That was our idea. Well, that just turned out to be plain wrong, for one thing, so our hypothesis was no good. But there's a couple things here that are really interesting. So when you look at all of these little images, this is just one transect. So I'm showing you the same transect over and over and over again, transect 3 about halfway down. What I'm showing you, if we just focus on one column at a time here, is a single tracer test. At one transect, what I see is 3 hours, 6 hours, 12 hours, 24, 48 hours into a 48-hour tracer injection. I have a whole bunch of salt in a little stream. And then what I also have is sort of a whole bunch of salt around that stream. So what I have is that salt has migrated into that hypereic zone, into that aquifer around the stream itself. And then when I turn the tracer test off, what happens is that the stream itself cleans up pretty quickly. We've seen that in multiple tracer experiments, but left behind is this sort of bathtub ring of salt. So here's the sort of transient storage piece of this system. The stream itself is clean again. We've turned the tracer test off, but there's still lots of salt left within our aquifer system. So if we're dealing with just in-stream measurements, we're missing a whole tail to these data because there's still a lot of material left in the aquifer. 48 hours later, it's largely gone in the system, but there's still some things there. When we migrate through here in time to smaller and smaller streams, we see very similar patterns, and in fact, we don't see significant differences here in terms of the size of that exchange zone here. A little bit, but it's hard to make clear interpretations. The stream itself gets smaller, so it's harder to see it cleaning up with later time. So what is a talk on geophysics without some 3D cutaway isosurface plots? So what I'm going to show you here really quickly is sort of taking these 5 transects. The one has no good data. You see it missing right in here. And what we're going to do is just take a look at what we see in sort of a 3D sense. So we have a tracer test. Flow is now going the correct direction from up here above the steep narrow valley going down through the flat wider valley. So what you're going to see is that we're going to step through this tracer test. This is 1 hour in. Already there is something funny here, right? Which is that already I see tracer 1 hour in down in the flat wide valley, but not up top. It's like it jumped the whole upper part of the aquifer according to the whole upper part of the stream system according to the geophysics. But let's migrate through in time. So this is 12 hours into that tracer test, 36, 48, 60 hours. One of the things that you do see is you see something that looks like there's splashback almost right here. There was a large downed tree actually at that part of the stream, and so I actually think that may even be just the result of that you're actually seeing some of that tracer as a function of the fact that you've got something blocking that stream a bit. But what we're seeing here is, and then this thing is migrating away, is that we're able to sort of image the stream and the flow paths around that stream in sort of a continuous way. Now, that's part of the story. We see this thing clean up. There's a couple of weird things about it. The fact that the tracer shows up downstream first is certainly problematic. But let's take a look at some moments. What we often care about when we're interested in tracer tests or in contaminant transport is the most basic statistics of that plume. So what we might be interested in then, if we look with concentration and time, and here's this red curve here is supposedly my data. If I have a concentration through time curve, then I can say something about things like the amount of mass that have passed a point, the mean arrival time, the temporal variance of that tracer test by just taking a look at this curve itself. So the area under the curve tells me about the mass, right? I can find this location that tells me about the center of mass, the spread that tells me about the variance, and those things are related to processes like advection is going to control the mean arrival time. Dispersion and diffusion are going to control the variance. And then I could think about higher order moments, like how skewed this curve is, the skewness, which is going to be related to transient storage. The nice thing about estimating moments is that they tell us about process, and also, in terms of temporal moments, the math is really easy. What this equation just says is that if I'm interested in the moment of some concentration history, I need to know basically one thing, the concentration with time. And that's it. Concentration with time we have as hydrologists. We do really well with that. The spatial piece is always hard for us, but temporal moments are easy for us to come by. So what we're going to do is we're going to take those images of the geophysics and we're going to calculate temporal moments on them. So what we're going to do is try to estimate mean arrival time and mass and variance over the entire aquifer system, which is something that we have a hard time doing otherwise. So here is mean arrival time, which is a function of the first moment. So a couple things that you see here, one of which is that this is a 48-hour tracer test. So the advective timescales, 24 hours would be sort of when we'd expect the mean arrival time to show up in the stream. And if we look down gradient in the stream, in sort of the flat, wide area, we actually see a mean arrival time in the stream that's pretty close to 24 hours. What we do see, however, is that as this thing gets whiter, it takes longer for something to arrive. We're seeing tracer much farther out than the stream, but it's taking a long time to show up. Up in the upper part of the watershed, though, we don't really see much that's very predictable. And that's kind of like when we were looking at the images, the isosurface images early, that we just didn't see much happening up there. And so the story in the upper steep, narrow part of the valley is just not that good, actually. You can see a little white spot right here. And I'm going to show you skewness next, because it turns out the second moment is not that interesting. If I look at skewness, I see that same sort of white area here in dark. That's that boulder. So part of the reason there's a very long mean arrival time, and we have here we've got no tails happening, is basically no tracer was getting past that boulder I pointed out. So just as a gut check piece for some of these data. But again, even in this skewness, which tells me about the transient storage piece of this system, what I'm finding is that down here in the lower part of the aquifer, I do a really good job of saying something, there's transient storage happening around my stream. I see this bathtub ring, and it's saying, wow, there's a lot of retention that's happening in this area right around the stream. Again, the upper part of the aquifer, I just don't see that much. So what's happening here? Well, I think that the geophysics is actually fairly limited, resolution-wise, in terms of what it can see. In the upper part of this watershed, where the stream is so small, this is a very small stream, and it's fairly steep, that tracer is moving by so quickly, and it's such a small target that the geophysics is actually doing a really poor job of recapturing that target. Geophysics electrical methods do a really good job of finding large diffuse targets. Small concentrated targets are hard for it to see. And so what's happening here is we're just not even seeing this tracer in the upper part of the watershed until it actually gets to a place where it slows down, spreads out a little bit. And then we're actually able to say something about process. So what this means to me is that we would do a better job, A, with slightly larger streams, potentially, but that we need enough time to actually have that tracer get into the aquifer. In terms of imaging tracer concentrations in a small stream, we do a pretty poor job. The other thing that I think is interesting about these data, though, is that there's long been talk in the world of surface water, groundwater exchange about the window of detection problem, which is that however long you do your tracer test tells you about paths that are associated with that length of test. So what I mean is that if you do a 48-hour tracer test, you're never going to light up the paths that are take more than 48 hours to fill, and how long do you keep sampling for this thing for? And so one of the things that I wonder with these data, and this is still just a thought that I'm having and now sharing with you, is what I'm showing you here in the open circles is the fluid conductivity in the stream for 3 different transects for 2 different tracer tests. So what you see at all these transects is that you see an increase in conductivity, and then you turn the tracer test off, and the stream basically goes back to a background condition pretty quickly. What I'm showing you in the little hatched marks is sort of an average of the geophysical data over those same transects. And so I'm showing you these as percent change. And you see that it takes a little longer for the geophysics to ramp up. It hits a different plateau. And then when I turn the tracer test off, just like you guys saw in the bathtub rings, I see these long sort of tails here. And so for how long should I be sampling and monitoring these things? Well, maybe the geophysics helps me figure out when to stop sampling. So I feel like there's a couple things that these tools provide for us. A blurry version of the subsurface, which is useful for a couple of reasons. Spatially exhaustive understanding of what's happening, and then also from a temporal perspective, maybe when to stop sampling. So that's it. That's what I have for you guys. So in short, let me just try to sum up what we talked about here today. So one of which is that I think that electrical resistivity is good for these sort of transient storage problems. We see them in soil science, we see them in groundwater, we see them in surface water, groundwater interaction. And I think that they can help us constrain some of the parameters that we don't know, and they also allow us to see in a way that we don't normally have data. And there's more to the story of groundwater surface water exchange than Mike and I's hypotheses. These are too simple. We didn't think about the fact that the stream flow itself is changing. I mean, there's a lot of things about this hypothesis that are too simple. Part of the reason I wanted to share it is just that it's wrong. I feel like sometimes it's useful to see people present poor hypotheses, so here is one example. And that flow rate is really confounding water table control, among other things. And so the images that we had in our head of what was going to control this simple system, we drew these 2D images without sort of thinking about the whole 3D picture. And lastly, while I think these tools are really useful, I think there's a lot of caveats to take away from geophysics. You're seeing sort of blurry images. You need these rock physics relationships like Archie's law to get back to parameters that you're interested in, and the quality of those relationships is important to understand. And that also, we can only image certain targets. Certain things are outside of the range of what geophysics can do, even when it can be a useful tool. And so just to keep in mind, in terms of using these tools yourselves or evaluating other people's data, that there are limitations that are just the truth of geophysics. So with that, I would be happy to take any questions. How did I do time-wise?
Questions? Yeah, Jay.
Fusion is probably occurring all the time, and it's not just turning off and turning on. And what do you think if you'd extended it for 40 or 60 days, or for this watershed for the city council, it's over the course of probably years, and how would it just flush out all of the salts then? And would you not be able to then see that effect?
Yeah, okay, so let me make sure that I'm answering your question okay. So the idea that diffusion is happening all the time is absolutely the case. I think part of the reason that we see that rebound is just because while diffusion is happening all the time, it gets to be a process that shows up when it's not quite as advective. Do you mean if I had stored that water for sort of 60 days instead?
No, if you continue pushing water through the system, so if the duration of the infection had been much longer, you could have exhausted your local storage capacity.
Yeah, I wonder about that. And so let me think about that for a second in terms of how to quantify that. But I suppose there is that possibility that we would eventually get rid of most of that mass that's in there. It would be simple enough to test with a model, certainly, as to whether or not that was the case. I guess it would be constrained a little bit by that mass transfer rate and then the length of the experiment that you're exploring. But it seems to me like that would certainly change depending on how long we'd have been injecting that tracer for. We think about similar things in stream tracer tests in terms of how long of a stream reach to consider, given the velocity of the stream. So it would make sense to me that we'd have a time piece that would go with that as well. So that idea makes complete sense to me, actually.
Students in class who might have a lingering question from this morning.
Please, Jim.
Jim.
If there's any connection between what materials would we expect to see mobile and immobile waters in? For example, what I'm thinking of is well-sorted versus poorly sorted, or maybe even Archie's cementation?
Yeah, so there's actually a whole world of interesting questions in that one. So we've been trying to do a lot of lab experiments, and one of the things we wanted to do was have simple materials to sort of test these ideas without dealing with real geologic systems, which are much more complex. And so we have well-sorted sands, which are easy and have very little less mobile pore space. But we were using zeolites, for instance, as a geologic material that's got a well-known dual porosity structure. And so we would pack columns with zeolites so that they were homogeneous, but still actually had a dual porosity piece to them. So we've been thinking a lot about what materials we could use in column systems where we can control something pretty well, while still having this sort of mobile-immobile type behavior. Certainly fractured rock, I know some people in here are working on systems like that, have the same sort of in soil science, connected, disconnected, but the level of heterogeneity is so high in those environments that it also makes it kind of difficult. So from a lab point of view, and I don't know if this is exactly answering your question, we've thought a lot about what materials we could use to produce this sort of behavior without having to get into the complexities. Vicor glass is another example that we've used. It's very expensive, and that's part of the reason we haven't done a lot with Vicor. It costs about $3 grand to fill a small column. But so we've thought a little bit about that. The other thing with Archie's law, your cementation exponent is a great question, because one of the things that I was wondering about was how to average the mobile and immobile conductivities in that connected and less connected pore space within an Archie's law type space. So when you think about Archie's law, it says there's a linear relationship between mobile and immobile, between the bulk and the fluid conductivities through this formation factor. And for the rest of you, this formation factor looks like porosity raised to a tortuosity sort of term. And the thing is that I was trying to make a dual domain Archie's law, and I couldn't figure out if things should be averaging in, in series or in parallel. And then there was always these assumptions of how does the tortuosity change between these two domains. And that's something I don't think that we can easily even measure. And so how tortuosity changes would impact the bulk conductivity I would expect to see. So not only do I have two different systems, the conductivity of the mobile, the conductivity of the immobile, I don't even think the tortuosities they don't have to be the same. And so the way to average these two things is interesting. So I've written a theoretical paper that waves its hands at how to average these things based on some mathematics, but I'm actually not sure that it holds in reality, because I think there's a lot of really interesting questions about what the cementation exponent does between connected and disconnected pore space. And I think that's open. I would love to see someone actually have those little pore scale measurements that could tell me about that. But I don't know the answer to that.
Andrew.
Just a question about temporal scales. Have you looked at what happens on very fine timescales with these electrical conductivity fields? Because there's so many variables, I think, that actually impact the resistivity or the conductivity. For example, temperature.
Yeah, absolutely. So two answers to that question. The first one, before I forget, is that everything here is temperature corrected. So we actually do take temperatures both on the surface and in the subsurface, so we can correct for temperature in these data, because temperature is a controlling variable for electrical resistivity. So we have to actually get that out of the data as best we can. But there are a couple of other things that are in there, like moisture content and the way the water table would be changing, that I think they're probably secondary variables in this particular set of experiments. With groundwater, it's easy, right? It's so far away from everything else. But in the surface water groundwater system, I think that's a really important piece. And I have long wanted to sort of model these data and take a look at what happens, because even on a diurnal cycle, on a daily cycle, you've got a water table that's going up and down in these watersheds as the trees are using that water. I don't think it's the primary thing that we're seeing, because we're bombing this thing with so much salt. The dominant change is from that. But I see it in the data. I can actually see these little tiny changes in resistivity associated with tree pumping. So I know that is a thing. In terms of how finely we can measure data, one of the things that was very challenging about this work was getting used to the fast rates of processes in stream systems. So as someone who had primarily worked in groundwater systems, groundwater is so slow that I could kind of collect data all day. When we started working in these systems, and I was talking to the stream hydrologist about how fast I needed to actually be able to collect data, they said, "Oh, well, what do you think? Can you get data every minute?" I'm collecting, sort of 400-ish measurements per reconstructed image. And that takes about 15 minutes to collect, maybe a little less. I think at some point I got that down to about 8 minutes. But there's a trade-off here between how quickly I can collect data and how quality of a reconstructed image I can make, because the more data I have, the easier it is to reconstruct that model. And so there's a trade-off here between having anything that's meaningful and collecting data that are fast enough. So in terms of processes, I think I can say quite a bit on things that are happening on sort of the hour scale, but anything faster than that is really hard to capture with these data. But I think your points about water table dynamics and moisture content are buried in these data, for instance, that we haven't captured. People have exploited that for other projects where they've looked at how moisture content changes have evolved under different seasonalities, under different ecotones. So they've looked at the rooting depths of different trees through season. They've sort of capitalized on these data. Here we sort of pushed it under the rug, but I think it's important, and probably secondary effect, but something that's important and should be explored.
Mm-hmm. I'm wondering how these would apply to transient saturated systems. So you've talked about groundwater and the stream, where you're in saturated systems.
Yeah.
I work on hill slopes where we apply a tracer, let's say a line source of a salt tracer or a deuterated water. And what we find when we get rain events, and it's a very non-steady state, you get a very much a pulsing behavior of the tracer. So the first rain event comes, and with it, maybe you'd get 10% of the tracer breakthrough along a hill slope the length of this room. But then slowly over time, the tracer's migrating through the unsaturated zone. It's hit by rain events, and each time you get a pulse superimposed on this slow kind of diffusive movement. And then after a month or two, you've got the majority of the tracer out.
Yeah.
And I'm wondering how we can tackle questions like that seem very difficult because it's non-steady state, it's saturating, it's desaturating.
And stuff is going.
Yeah.
Yeah, in terms of an imaging problem, it would be a very fun one. There's a couple of things that would be complicated, but I don't think that would make them undoable. So it's one of the things, part of the reasons that I've been kind of loyal to electrical resistivity as a method, as opposed to other geophysical tools, is that it's really good for time-lapse work. And so you can put electrodes out and then leave them there for a season or a year or 3 years, 5 years, put the box out in a little doghouse and then go have a beer. And so it's easy in that you don't have to move things around. So for those of you that have used ground penetrating radar or electromagnetic methods, they usually require someone moving pieces around, so it's very time consuming. So you could, on a hill slope like yours, instrument this thing up with a bunch of electrodes. Now, I would say that the top 10 centimeters sort of all averages together. So you'd be interested, hopefully, in things that are a little deeper than that, because the electrodes themselves go in the ground a little ways. You would certainly image these changes. The things that you would have to separate out are probably changes in moisture from changes in salinity. Those would be two things that would be pretty hard to parse, but maybe you don't care at some level. Maybe you just need to know where stuff is moving, and whether it's saline or it's just wet, doesn't matter. So you could just look at rainfall, for instance, in which case you just wash out the salinity data and just say, well, you know what, it's mostly moisture that I'm interested in, maybe. And so you could potentially watch these things migrate. It'd be, again, sort of this beer-goggly version, but I do think that that's something that would be feasible, at least.
Right.
And over long, long periods of time, you could just have something out there and listening and watching.
Good. Well, we're just on 5 o'clock, and I'd like to thank Kamini for really opening our eyes to applications in hydrogeophysics. Many of us are going to walk to Alexander's now, invite anyone who'd like to join us to have a beer with Kamini and pick her brain further on hydrogeophysical approaches. So thanks very much.
Thank you guys for your time.